A Subaru Outback 2.5 liter engine has a maximum power potential of 170 horsepower. And we can multiply that by, about 3/4 of a kilowatt per horsepower. Yields about 127 kilowatts. Okay. It goes from 0 to 60 miles per hour in 9.7 seconds, right? And we remember that 60 miles an hour is about 27 meters per second. You can convert that. And its mileage is about 30 miles to the gallon under highway conditions. Okay, the mass is equal to about 3,500 pounds, but there are, in a kilogram, about 2.2 pounds. So we end up with 1,600 kilograms, or about 1.5 tons. So let's find the energy it takes to accelerate up to this 60 miles an hour. We know the kinetic energy is 1/2 mv squared, which is the 1,600 kilograms times 27 meters per second. Yields, in a kilogram meter squared per second squared is a joule, and we get quite a bit of them. It turns out to be about a little more than half a megajoule. Okay, a little more than 500,000 joules. And we want to find the amount of time it takes to get this much energy from our engine. And we remember, power is equal to the change in energy. In this situation, the change of kinetic energy over time. So the change in time is equal to the power. The change in time is equal to the energy divided by the rate at which you provide that energy, which is the power, and winds up being about 4.5 seconds. So we want to find the acceleration under this condition. The acceleration is equal to the change in velocity over change in time, and that's going to be 27 meters per second divided by that 4.5 seconds. And the units are meters per second squared. I love it. And the numerical number comes out to be about 6. So you got about 6 meters per second squared. And you wonder, what is the angle my fuzzy dice are going to make as they hang from the mirror? So if we look at my fuzzy dice hanging from the mirror, we know that this car is not accelerating because the force of gravity downward is equal to the tension upward. If we were accelerating, the dice would look like this. It would swing. It doesn't swing back. What happens is the acceleration is in this direction at 6 meters per second squared. It's being pulled forward by the tension in the string, and the force of gravity is downward. And then we remember, if the acceleration is in this direction, the sum of the forces must equal mass times acceleration in that direction. And so we take a look, right. So the sum of the forces, we have tension plus the force of gravity is equal to mass times acceleration. And again, we make it so that this is a right angle because the acceleration is horizontal. And so we want to find this angle. We don't know tension, but we do know the force of gravity and we know the acceleration. So we like it, so we pick tangent. Tangent of theta is equal to opposite over adjacent of apples, right? Mass times acceleration, mass of gravity. These cancel, and I end up with about 0.6. And so if we solve for 0.6, the arctan of 0.6 is about 31 degrees. Now, you can't get, so why is it that this 4.5 seconds is much less than the 9.7 seconds that the car actually takes to get to 60 miles an hour? And it's because we don't get that maximum power from our engine all the time. There's two things to consider. One is power is equal to work, the rate of work, so work divided by time. Work is force times velocity divided by time. Force times displacement divided by time. And displacement divided by time is velocity. So the power that the engine puts out is the force it's providing for you times the velocity. At zero velocity, at very low velocity, could the force be close to infinite? It could be very, very high. And we realize it can't because you're going to have friction on the wheels that's determined by the coefficient of friction. And so you just would not be able to provide that huge power. But furthermore, the way gasoline engines work is you get almost zero force out of the engine when they're spinning slowly. That's why we worry about stalling our cars out when we slow way down. And so your maximum, if you look up the power, the maximum power is produced around 5,000 RPMs. And so we only get this maximum power delivered to the wheels at certain conditions. And so in accelerating, there's sometimes you're getting much less than maximum power. D. How about we find our use of gas? And so we want to take a look at the car because there's a way that students did it that was very wrong. Is they used their kinematic equations to find the acceleration distance, 1/2 at squared. And then they said, oh, okay, then I use my mileage because I know mileage is equal to the distance you go divided by the amount of gallons you use, the volume you use. So the volume would be equal to this distance divided by the mileage, right? However, this mileage was calculated on the highway going at a constant speed. And so we think about what is the energy that we put into our car if we accelerate over this distance. We provide a force, so the force of the engine, or the work of the engine, what does it do? It changes the kinetic energy by speeding it up, and it also compensates for the work done by friction, because there's some frictional force pulling back. And I argue that this kinetic energy that you get in accelerating is way, way bigger than the force of the engine due to friction. And this we know because when you're driving at a constant speed on the highway, you can hear the engine is barely laboring. But if you accelerate as fast as you can, then the engine is laboring very, very greatly. And so this is the largest consideration. You could also consider this, which we will do later. But if we want to find out how much gas we need to accelerate to 60 miles an hour, what we want to do is say, oh yeah, I remember that the amount of energy I used, changing kinetic energy, is about a little more than half a megajoule. I think I got 0.57 megajoules. And we remember that gasoline has an energy density of 125 megajoules per gallon, or 46 megajoules per kilogram. I'm sorry I told you 48 in class. It's actually 46. And you'd say, oh, then how much do we need to provide this energy? But this is the energy we need to get out of the engine. Remember how an engine works. We put gasoline in, and we get work and heat out. And we remember the efficiency, which is about 25% under maximum load, is equal to the energy out, right? This kinetic energy that we get out of the engine to the wheels, divided by the energy we put in, which is the energy of the gasoline. And so if we want to find the energy of the gasoline, we have to take the energy out, which is this, and divide it by that 0.25, or multiply it by 4. And we end up with about 2.3 megajoules. Okay, so if the energy is equal to 2.3 megajoules, that's the energy of the gas, all we need to do then is divide by this 125 megajoules per gallon. The megajoules cancel, and I end up with about 1/50th of a gallon. I think I get 0.018 gallon, right, which is a little bit less than 1/50th of a gallon. And you ask yourself, does that make sense? That means 1 gallon of gas would allow you to accelerate up to 60 miles an hour 50 times. Seems reasonable. We could also express this in kilograms, and that would be on the order of 0.05 kilograms, or a 20th of a kilogram.